In this video, we'll talk about what are the consequences of heteroskedasticity for our OLS estimators. Now, recall that we've talked about the 5 Gauss-Markov assumptions for OLS regression that we need. And this is saying, we need linearity in parameters, we need random sampling from the population, we need no perfect collinearity in our sample, we need our 0 conditional mean assumption to be satisfied, and we need homoskedasticity. Okay, now the nice thing under these 5 assumptions is that our OLS estimators are blue, which is to say these are the best linear unbiased estimators. Okay, when we add the assumption of normality, and we covered this in chapters 3 and 4, the tests that we conduct, the t-test, the f-test, and the confidence intervals that we construct are exact for any given sample size. Okay, so we were able to conduct statistical inference nicely. Okay. However, even without normality, in case your sample size is big, which is usually the case with a lot of the data that we use, and hopefully you will use for your projects, the OLS test statistics are, and the confidence intervals are asymptotically just justified. So as n tends to infinity, or as your sample size becomes very large, these test statistics and confidence intervals tend to be exact. Now, the problem is what happens, when we encounter circumstances where this assumption of homoskedasticity is violated. So what happens when there is some presence of heteroskedasticity, or there is non-constant variance in your errors? Okay, so here we're basically saying what happens if the variance of u given x actually depends on the value of x, right? It's not equal to a constant. So as the value of x changes, the variance also changes. One implication of this, which is good for us, is that the OLS estimators are still unbiased and consistent, even if this homoskedasticity assumption was violated, because recall that for these we only needed the first 4 assumptions to be satisfied. Okay. So remember that heteroskedasticity does not cause any bias or inconsistency in our OLS estimators. Okay, so let's think about what does it do then, if this is not troubling us when we think about unbiasedness or consistency. Where heteroskedasticity does trouble us is when we think about efficiency. Okay, so with efficiency, we mean that we're thinking about the variance of our estimators. Okay, so we're thinking about the variance of our beta hat j's. Okay, and this guy, recall from your formulas before, that this actually depends on the variance of u. Okay, so because there was that sigma square in the formula, this is going to be affected if the variance of u given x is going to be different for different x's. So in other words, when heteroskedasticity is present, OLS estimators are no longer blue. Okay, so we are in fact able to find unbiased estimators that have smaller variances than what OLS produces. Okay, and this has implications for efficiency of our estimators. The more important piece here is that when you have heteroskedasticity, the usual standard errors of our, remember that we can construct standard errors. If we know the variance of beta hat j, we can construct the standard errors of beta hat j. Those are no longer valid, which means that when you think about your t statistic, which is your estimated value minus your hypothesized value divided by the standard error of your estimator, if the standard error is changing, the t-statistic is going to be changing as well. Okay, so the t-stats, the regular t-statistics that we have under OLS don't apply or become invalid because this standard error is changing. Okay, and this is also true in large samples. Similarly, when we are conducting joint hypothesis tests using the F statistic, those tests are also no longer valid in the presence of heteroskedasticity. So in other words, we're basically saying that heteroskedasticity has implications for statistical inference. Okay, it can invalidate the regular statistics that we use. And maybe even change the significance of these T or F statistics because this standard error is changing. Now, without the homoskedasticity assumption, there are good reasons to use OLS. Many papers would still use OLS, but we can always modify the usual test statistics in a way to make those valid in terms in the presence of heteroskedasticity. Okay, so this is really easy to do when we will code it, but you need to understand what's going on in the background. So we're not going to be constructing a new estimation method, but we're basically going to do what is known as heteroskedasticity robust inference for our OLS estimation. Okay, and I will teach you how to do that in R. But before we go there, remember that, many times it's incorrectly claimed that R square and the adjusted R square that are produced using OLS are no longer valid in the presence of heteroskedasticity. Okay, this statement is untrue. Okay, this is untrue. Both R square and adjusted R square remain consistent estimators of the population R squared. Okay, and the reason for this is that the way the R square is constructed is based on the unconditional variances of U and Y and not on the conditional variances. Okay, so that's the idea here. And then in the next video, we will talk about how to conduct heteroskedasticity robust inference.